So,
thanks very much for the very handsome introduction, Marian. Do you hear me?
Yes.
Okay, so first of all, I would like to clarify, I never worked for Hewlett-Packard. I spent 4 years for Intel Corporation, and the last 2 years I was working for the company, which is the small startup, which is called Graphcore. But in addition to my professional life, I have also the academic one, and this is something which is more provocative in today's talk. So I would like to merge together my professional experience with the area of my academic interest. And as is my first introduction talk to the Sano participants and the Sano users, I would like to give you some overview what I'm looking for and what I was doing during some of my period at Intel and the Graphcore, and see if we can find any common ground in the area of collaboration, especially on the field which we use every day, but sometimes you are not aware that how important this component is. I'm talking about the computer arithmetics. Everybody does this operation, but some the people are not even thinking so much how important they are and how much we can get out of this computational arithmetics operation to increase our computational big science. So before I will start, I would like just to discuss with you why the computer arithmetic is important. So computer elementary and transcendental function are highly useful in every engineering fields, particularly if you look on the any digital signal processing type of the devices or the machine learning type of the devices, like for example Graphcore was, or Graphcore still is, but I was working with the Graphcore. The transcendental and the fundamental functions are the key components for the major of the operation system is going to use it. And if you look on the IoT type of the devices, small microcontrollers, and any type of the tiny type of the devices where you don't have this luxury to use the implemented by hardware transcendental and elementary function, this computer arithmetics is going to be even more important. And because as we know, most of the participants may have some experience with the high-performance technical computing. We have the big list of the physicists, and they made the experiment which we are running right now in the CERN. And of course, because we are in Krakow, we have the Cyfronet, and we have the collaboration with the CERN. On the Large Hadron Collider, 25% of all the simulation time was spent on the elementary function. So just imagine, if you can increase performance on the 25% of the operation, which you are running every second, you can get the big performance gap and the big performance boost. So this is the importance from the one hand. So we are using them. Even if we are not thinking about them, they are very important in any scientific calculation. Second important element, which I would like to bring because of my Intel experience, I joined Intel in 1996, and probably some of us are familiar with the most important bug, which was found in the 1994, 1995 in the Pentium processor. I know it was in the previous millennium, but in fact, in my opinion, it was the most important event in the whole Intel industry. On the history, Intel just demonstrated to the industry how it can handle the critical situation. And in fact, it was, a lot of jokes about it. It was a lot of history behind this very important bug, which was very crucial. And I will tell a little bit about it. But basically, if you look on this bug, for some of the people who are not familiar with, in the 1995, Tom Nestle found that if he is doing the sum of the reciprocal of the prime numbers, he's getting some uncertainty and some elements which are not calculating properly. In fact, the Pentium processor, when it was doing the division operation on some prime numbers, it was able to provide just only the 14 bits precision. So if you just look on the single precision format based on the IEEE 754, it was the 10 bits less than the official format was provided. So in the addition, it was not just only a degradation of the precision, but it was a lot of uncertainty connected to this simply operation like its division. In fact, it is not the simply, but we will get back to this operation later on in the talk. And here you have the couple of the interesting Intel responses to this crisis situation. I need to say that I joined Intel exactly when the Pentium with MMX technology has been announced. So just 1 year after this big crisis happened to Intel. And what you can see on the screen is this couple of the interesting statements made by Intel during this time. And in fact, they were also creating some kind of artificial words, instead of bug, they were using the errata. This is the most favorite statement at Intel. So we don't have the bugs, we have the erratas. And they were just saying a couple of interesting, we'll redefine the PC and the math as well. Why you think it is called floating point? And, division is the very complicated operation. So this is the couple of the statements I took from the press during this time when we observed this Pentium crisis situation. But of course, it's not just only the funny thing, and the problem with the divisional component in Pentium almost 35 years ago. But 25 years ago. But let me say that this incorrect operation may lead you to the disaster. This is one of the examples from the 1991 when the American Patriot missile battery in the South Arabia failed to intercept the Iraqi Scud missile. Consequence of this, it was death of 28 people. So basically, because the finite precision, the precision of the calculation unit inside the operation code was not precise enough, the consequence was very serious, And if you look on this particular report, they were just saying the software problem. What was the specific of this software problem is the very simply, then the integer register is just only, as I said, 24-bit wide. And when you are just doing some kind of the clock conversion to the seconds, you are just not able to store the proper number of bits. In consequence, because of this, during the 100 hours operation period, we cumulate something like 0.34 seconds of the unprecise calculation. If you just imagine that the Scud rockets is traveling with the 1067 meters per second multiplied by this 34 seconds, you are missing the target by the something like 570 meters. Consequence, the missile was not intercepted and the American soldier died. And this is not only the example of this type of the situation. A very similar situation was also led by my favorite French colleagues. They were building the Ariane rockets for the European Space Agency, and they just do some kind of unprecise floating point conversion to that, which was kept instead of the 64-bit in the 16-bit signed integer. So as the consequence, this rocket was exploding on the 3,700 meters consuming something like a $5 million rocket. I'm not even mentioning how much cargo it was cost, and the developing time, and the budget was around the $7 million American dollars. And of course, how the French guys nicely answered this, it was the software error in the internal reference system. So this is the two examples what computer arithmetic can do if it's not properly handled. And if we look on another slide, which is basically saying about all the aspect or the topics computer arithmetic is involved, you need to take into consideration is basically two fields. We cannot discuss the computer arithmetics just only software on the hardware. These two fields are, coexisting each other, and they are crossing, and they are some kind of in the symbiotic world. When you are trying to build a new numerical method to solving some numerical aspect using the computer arithmetics, you please remember that you are always running this on the hardware. Of course, we can take into consideration that this is a classical CPU or is there a GPU, but CPU and GPU, they are two different hardwares. They are handling completely differently the computer arithmetics. When we are talking about the microcontrollers, when we are talking about the ARMs, when we are talking about the IoT devices, all these arithmetics, even if they are running the same code, they don't have the same type of the capability. They are not going to provide exactly the same answers. So always when we are just talking about the computer arithmetics, we need to take into account that we have the two worlds. One of them is the hardware and one of them is the software. And two of them, they need to coexist and they need to be taken into consideration when we propose something.
Paweł, may I interrupt you just for a while, because after such disasters, I think that there should be one effort oriented towards understanding what is going on. On the other one, do you know something about some, let's say, let's call these theoretical methods of analysis of how floating point operations precision is very important for this?
This is exactly what I was saying. It was in this particular report of this rocket, we know exactly what was the root cost. The root cost, it was the wrong representation of rounding around the and conversion around the numbers. So it was the basic human error. It was not the hardware. It was the human error in the algorithm. Somebody said, okay, let's keep this number because it's small enough in this precision. And unfortunately, during the cumulation of the time, the error was bigger than we can store it in the particular data format. So it is very well reported. And during the hardware implementation of the basic operation, as I'm going to say, is the pretty obvious, It's not the big deal how we are doing the fundamental operation like addition, This is not a very complicated basic module, what you need to do it. You just need to shuffle the bits properly. The same with the subtraction, which is, reverse operation to the addition. But if you look on the multiplication, for example, the circuit design, which needs to handle all the aspect of the multiplication of the two numbers, is the more complicated. And of course, when you are just talking about the division, the operation is even more complicated. If you add to this fuse, multiply, and add type of the operation, when you can parallelize some of the basic computer arithmetics operation, is going to be even more complicated. So what else we can do in the hardware, and what else can we implement in hardware instead of this, basic operation like addition, multiplication, division? Some of them can be implemented of hardware, but is always driven by the sum of the compromise. So what we can implement in hardware, for example, something what we are calling transcendental function. Transcendental functions are very complicated to calculate, and it's better to have them in hardware. Thus, every hardware has the transcendental function implemented. Answer is Of course not. And as I said, the luxury, of course, the basic allo operation, as I was describing a few minutes ago, are pretty obvious. But for the transcendental function, we have there some kind of dilemma, what we should implement and what needs to be executing software. So this is the example of the function. I was working for the third generation of the chips at Grafco, which we were looking for the hardware implementation. But before we start, what are the elementary and transcendental function overall? What is the definition? So in the math, the elementary function is the function of the single variable. You know, it could be the typical real or float or the even complex number, and is defined as the sum of the products which are based on the fundamental arithmetic operation like sum, addition, multiplication, division, etc. Transcendental function in math, the function which cannot be expressible as the finite combination of the algebraic operation. So if you cannot do the some kind of if you are not able to build the sum of the formula which contains the the subtraction, multiplication, division, raising to the power, and express your function, we are calling this function is transcendental. So you have the example of the transcendental and the algebraic type of the function over here. So again, transcendental function are the function which are not expressible for the finite combination of the algebraic operation. So very simply, algebraic operation when you have the multiplication, squares, and the division, and there's some example of transcendental function which you cannot express as the combination of them. So the next question is, why do we need transcendental function? For the very simple reason, we need to have something which is calculated very fast. And as you will see in the future, in a few moments, the calculating transcendental function is not something simply. Secondly, what is even more important and why I was looking for it, or why I was deeply involved in this process, is that we have the explosion of the machine learning, artificial intelligence, deep learning, and all the stuff which is around us. And without transcendental function fast execution, we cannot think about it. So if you are building the hardware for the machine learning, deep learning, and AI, and if you don't have the sum of the transcendental function efficiently handled, you're probably out of the market. And for example, softmax layers to compute probabilities, they are heavily, using the transcendental function. The same, the logarithmic for the calculation, the cross entropy are also based on the transcendental function like logarithm. And you can imagine that everything what you are running, the BERT or whatever kind of the model you are just thinking about it, is the heavily based on the transcendental function operation. As I said on the beginning, CERN, 25% of all the calculation time are spent on the transcendental and the elementary function. In some of the machine learning and AI type of the operation, when you basically do the linear algebra, this percentage is even higher. Okay, so what is the option? So why do we need to have the separate hardware, or is there any other option to do it? Basically, you have the three components which you need to take into account. First of all, we need the elementary function and transcendental function, the hardware wired for the two reasons, for the speed and accuracy. Of course, is some cost related to it, which is the extra area of your die. So if you look on your tile of the CPU, you just need to remember that if you would like to implement those functions I was just mentioned over here, some of them, not all, but just look on the single and half precision, for example, you will need something like 15% more space on your die. is the CPU, GPU, IPU, ARM processor, x86 processor, that doesn't matter. If you would like to do it in the highest precision, it's even more. So it's the always trade-off, you know, you just need to take the decision, okay, what I'm really going to implement in the hardware and what we can handle in software. In some case, if you have the very small devices, you don't have this luxury to implement this in the hardware at all. So how can we do this stuff? So how the computer arithmetics methods are built? Basically, it is very simply, you have the fundamental algorithms. They can be implemented in the software or in hardware, or in both, in fact, you know. There are three main calculations. First one is the iteration. Second one is the lookup table and interpolation. And the third one is approximation, or piecewise, or the approximation methods. So if you just thinking about any of the function, elementary or transcendental, basically you have the three methods or combination of them or some other tricks, which I'm going to show you in a few minutes. So what is the iteration method? Okay, let's start with the simply division mechanism and how we are doing the division of the two floating point numbers. If you just look on the division of the two floating point numbers, which I have over here, you know, you just see that is the mantissa and they multiply by the exponent. And of course, the most important part is how we are doing the division of the two mantissa. Of course, division is not the transcendental function, as you may imagine. As I said on the beginning, transcendental and elementary function, I basically take just only one argument, and here you have the two operators, but nevertheless it's very hard to implement this properly. And how we are doing this in hardware? So we are dividing two floating point numbers. So we just reformulate this, that okay, in fact we just need to take into account that we need to divide the mantissa, you know. The rest is pretty much simply as you can see, it is the power of 2 with the and the some subtraction. So of course we are starting with the conversion this to the multiplication. So we have the mantissa represent as the multiplication, and if you are just look on the reciprocal type of the function y by x, you just need to find the place where exactly this function is the root cause of the one of d. So something which is, you know, crossing the line of the axis x. And of course, how we are doing this, instead of doing the traditional way, we are trying to express this end or 1 by d by the Taylor series of approximation. So basically we are trying to approximate the place where is going to take the 0. So we are finding the root of this function where it's close to 0. Then we are trying to solve this for the h. You know, through some iteration steps, we are going to the situation when we have this formula, which basically is very simply to calculate, because what we have over here, we have the just only multiplication and subtraction, which is much easier than the division. If you just think about the division operation versus multiplication, it's completely different world, but we will come back to this topic on the real life examples, which I'm going to show you, because this type of approach is not the actual any longer, to be honest. And I would like to share some latest founding I got it and share this with you. So we know how to can do it. So basically, when we just need to do the two mantissa division, we can use the Newton-Raphson iteration scheme for the approximation 1.d using the Taylor series of approximation. So we have the very sufficient formula just to calculate the estimation of the x1. And the initial estimation for the starting point, we are keeping in the lookup table. So basically, we have some kind of the matrix where we are storing the initial points for the approximation. And through the calculation of the 1 by d, which is the x1, and multiplied by n, we can get this type of the formula, which is the very easy to calculate, just only multiplication and subtraction, and not any other operation which are needed. And what is the even more important, just to get this division, you just need to have one iteration, just one Newton-Raphson iteration, which is the lot of multiplication, but you are just running this once. And as you may see, this type of the iteration method gives very nice results in terms of the division operation. Another type of the algorithm which are used very often is the lookup table and interpolation. So basically, let's look on the logarithm, which is the typical example of this, how we are calculating. Just imagine that we have some kind of the argument, which is 8. We have the mantissa, and we need to represent mantissa as the multiply by the exponential, so it's a significant part. So through the some numerical operation, we are ending to the situation that we are just need to calculate the mantissa logarithm, and the rest is basically addition of the significant part of this calculation. And of course, how we are doing this, we are using the lookup tables, so we are storing some elements for the mantissa calculation. Of course, not every mantissa is stored in our lookup table. We are just doing some additional tricks just to minimize the space what we are keeping in the tables. So we are keeping in the tables just most significant bit and the offset, which is on this slide, and through the some type of the splitting the mantissa to the most significant bit and the index plus the offset, we can get this argument, so offset and the value of the most significant bit over here multiplied by index, and we are getting the mantissa. So this is basically how we are getting to this value, as you can see over here. So we don't need to keep all the values over here. We are just keeping the most significant portion in our table, in our matrix, and then we are calculate the less of the less significant bits, which are calculate from the output as the multiplication of the index and the stored value of all. The third one, I don't want to go to this very academical discussion, but the third one, so we know we have the iteration, we have the lookup table methods, and the third one, very popular, is the approximation, and especially the piecewise approximation. So basically, if you look on this type of the function, we are just break down the ranges of the boundaries of the function we are trying to approximate, and we are finding the most appropriate approximation method. Is very often based very often on the empirical studies. Is there a lot of studies made on it, and we are trying to find some kind of more important segments if the function is, somehow replicable. We are trying to do it. In this case, for example, we don't need to take care of this portion, because as you can see, we are just interested in this portion because this is just only different in the sign. And as you can see, we are just going from the 0 to the infinity, and we have some type of most important range and the special approximation type of used for it, and based on the different techniques, the different models, the different approximation function, we are trying to find the best range or the best function for the particular range, So for example, if you can see on the from the this range is basically the X itself, so the inputs is very easy. It is easy to calculate. This one is not so easy to calculate any longer, but if your number is small enough, you will get the very quick answer, because this piecewise approximation method is very important. And of course, as I said, we are very often trying to do the polynomial approximation using the various techniques. Very often we are using the magic number You may be aware of this particle approximation method from the Quake. It was the revolutionary approximation magic number type of the algorithm, but this type of the bits manipulation techniques, magic number, piecewise approximation methods, they are combined very often in the piecewise approximation algorithms. And of course, we don't have the free lunch. Something for something, nothing for nothing, as one of my mentor, I think, used to say. And in the iteration, we have some proofs and cons. And of course, iteration methods are very good for the wide range of the input values. But as you remember from this division, it requires a lot of multiplication, especially if you have the polynomial type of approximation is the x raised to 4. So you just need to calculate do the 4 multiplication of x, for example. Lookup table and the interpolation is very fast because everything you have stored in the lookup table. But of course, it costs a lot of resources, and they are limited applications, especially to this, which are have some kind of nice characteristics. So you don't need to keep the full range of the lookup table, but if your function is replicable, you know, in terms of the interpolation sectors, the lookup tables methods are very good. And piecewise approximation, it is the very good techniques, but if you have the different ranges for the different piecewise regions, it is going to be very complex. Is a lot of ifs and is a lot of conditional operation which you need to take into account. So this is basically the background and the foundation I would like to give to everyone before we start to discuss what we can do it, you know. So why do we want to improve them? All those techniques. We have the 3 methods. We have the, you know, the 3 or is the hundreds of them, but 3 basic ones. And why we want them to improve? First of all, system with the limited resources, like for example, IoT, all the, you know, the edge 3D graphics components, they don't have the luxury of hardware implementation. So you don't have the efficient hardware implementation for the particular function. Because if you have the something implemented in the hardware, don't try to win against with the software version. Even if it's not the ideal implementation, because very often the implementation you may find in the hardware is not the optimal or not most sophisticated version of the algorithms you have, but you don't have the chance to win against this with the software because you have so many conditional situations which are going to be some overhead for this type of the calculation. So yeah, secondly, classical algorithms which you can find in the hardware are not very often not optimal for the small devices. No, they are not even optimal for the huge devices, but because they have the very proof records of the validation, they are very often the most preferable algorithms to be implemented in the hardware. The second question is, do we really need full precision? Of course, when you are raising the missile like a Patriot, especially in our case, I mean the Poles, is better to have the better precision or bigger precision. There are smaller ones. And we need to take into account that the microarchitecture of the devices is evolving, and some statements which were very, you know, popular before are not actual any longer. And it's very often important to exploit this. And I have one of the example which I'm going to share with you when I will try to show you that, you know, something which was, you know, taken as the, you know, root of thumbs is not any longer valid one. And sometimes you need to revisit because the microarchitecture, you know, is evolving very quickly. So let's start with the first example. So we have the modern method for computing the square roots. probably one of the most popular transcendental function you are implemented. So it's the square roots. So what you can find how the people are calculating square roots. Most of the components you find on the market, they are based on hardware implementation, and they are based on the lookup table and some Newton-Raphson's type of the approximation with the Goldschmidt algorithm or something else. Is there tons of them, but they are very efficient because they have the lookup table. They are consuming some portion of the silicon, but for the square root to us is the very important operation. It is the very efficient solution. It's completely different with the cubic roots, for example. Not so many devices except processors are using the hardware implementation of the cubic roots, but this is another story. But in the direct lookup table solution, we have some other techniques like low degree polynomial type of the solution, multiplication based on the Newton-Raphson method with the some seed generator and the lookup table instances. We have the magic number constants, as you may remember from this famous Quake Arena square root calculation method, which was used mainly for the graphic components. Quarric method is the linear convergence is very slow there, and you have the multivariables methods which you may use for the calculation square roots. But let's start with something which is very basic, and this is from the Einstein, this is the Heron formula. Probably all of you all remember this from the secondary school, how you can approximate the square roots of the given number. The problem with this, it was this main disadvantage of the Heron formula, is that is using the division operation. As you remember from my initial discussion, the division is not the trivial operation either. So the people were trying to avoid any division if you calculation, and then they were saying, okay, traditionally division is the 40 cycles, and when you are doing multiplication and addition, you have just only one cycle. So just imagine you need to do the 40 multiplication and addition just to be on the one division. Yeah, but it was during the time when the first microprocessor and the first chips were launching on the market. It was also, it is something what we really teach also at the university level till today. Try to avoid the division as the very complex and the cost operation. But is it really true? What do you think, guys? I would like to be a little bit provocative, so this is my question to you. Do you still believe that the division and the Heron formula is the something which is still valid, or it is the absolutely academic antique type of the solution which we cannot take into account? Let me show something. Do you see my screen? Guys, do you see my screen?
Yes, we can see it.
Okay. So the first example is this code. What I have over here is basically the code which is calculating the square root using the various techniques, using the most widely available libraries, and comparing this with the other algorithm in terms of the speed, accuracy, and of course the precision, yeah, in the sense of the accuracy. So let's compile the code and then discuss, yeah. And I am running the code, which is I will come back. Do you see my screen of the code? I suppose. Yes.
Mm-hmm.
Okay, so what I have over here, I have the values of the different implementation of the algorithms for calculating square roots. And of course, started with this very basic Boolean. I modified the Booleans a little bit. The Heron, which was introduced by Miller, and Miller is some kind of the fundamentalist, is the Jack Dangara for the numerical arithmetics, let me say. This is the role the guy is playing. And of course, we have something what we are using every day. So we are calling the hardware implementation, which is taken from the math or CMath, C library or whatever library you are going to use. But it is classical Newton-Raphson type of the calculation with the huge lookup table implemented in the hardware. And if you can use a look on the sum of the source code of the hardware implemented, is the very simply and nice command. If you have the hardware version of it, use it. Otherwise, run this in software. And I will show you how unofficial it is. So, for example, you have this different type of the codes. Here I have the time of run. Please remember that this is the run in the whole range of the floating point number. You know, every representation of the number which is normalized divide by the number of the iteration. So basically, even if the runtime is not the correct one, because it's a lot of overhead, we are getting the very good result in terms of the nanoseconds, because we are running this on the whole range of the numbers, normalized numbers, and divide by the numbers of them. So here you have the time. Here you have the something which is more accurate. So instead of the time, we were just using the hardware pointers, and we were calculating the cycles. So this is how many cycles you need to calculate particular code, you know, on the full range of the normalized number. Here you have the, you know, correct bits, maximum relevant error, and minimal. And here you have the RMSD, which is the root mean square deviation. So it is basically the calculating how accurate you are comparing to the standard calculation of the defined by the IEEE. And what I would like to show you that the methods which are not based on the divide or Heron formula, they are my algorithm over here. You know, you have the for algorithm where I was using the multiplication and addition operation only. We can come back to this later on. You know, and here you have the something what I was just using the Heron methods in the different modification. In terms of the time, you see that, you know, I'm not so far away. You know, you can use it the 3 cycles, and I was even below the 3 cycles. You know, when I'm just looking for my most efficient one, so SQRT Heron with the 16 segment, which is basically the Heron formula with the piecewise approximation model, when I finding the different magic number for the initial approximation, they are, you know, the more efficient than this 23 bits, and you know, is the twice more efficient, even if I'm using the 2 division in this calculation. So if you look on the bit of the correct bits, my most important one was able to provide the 23 bits of precision, and the 23 bits of the precision I was able to get also without division, but the cost of it is the twice more longer. So is the statement that, you know, division is the very cost and the resource consuming resources algorithm still valid? As you can see over here, not. Of course, if you are just going to the standard hardware implementation of the SQRT, you see that, you know, the code is almost 2 times or more than 3 times more efficient than my software-driven calculation. So as I said, that what is this exercise all about? It is that, you know, not because the architecture is evolving, that all the statements we know from the past that, you know, division is not, please don't use it, it's not the right one operation because it is going to cost you a lot. It is not basically the truth. What I also would like to show you, if you just look about, this is the hardware implementation, but if you don't have the hardware implementation or your system, and you are using, for example, the Sun microsystem, some people may remember the Sun microsystem company, at least Professor Kitowski remember, that, you know, to calculate with the same precision, they were requiring the 223 cycles versus something what the Heron or my version of Heron can do it in the 4 cycles. Interesting? Yeah. I hope it is. And, you know, if you look on the same software version of the hardware implementation we have over here, you will find SQR alt and SQRTF alt. They are something like 12 times, 15 times more expensive if you are running the same algorithm implemented in hardware by truly software. And mine is purely software driven. It is no any lookup table. It's just only the Heron formula, which is over here. 2 seconds. Code is very naive. This is the 2 seconds. This is modified the Heron. This is the classical Heron formula when you have the 2 divisions, the line of division. I just changed the initial approximation to the more appropriate number and doing the second modified Heron formula. My most efficient algorithm is over here, 16 segments. This is my 16 segments version. When you have the different initial approximation tables over here, you have the tables over here for the initial approximation, which are taken to the different piecewise segments of the approximation regions. And it shows that the only thing what you need to do, it is to store this in the software, not in the hardware. And you are just 4 cycles instead of the 55 cycles. This is the first example. The second example is also very interesting. At least I hope it is interesting. So is the logarithm, you know. A logarithm is widely considered as the very complex and expensive operation to be implemented in the microcontroller FPGAs. And of course, in the CPUs, we have the logarithmic function, which is basically hardware implemented. And the most popular algorithms, the same way we have the piecewise approximation algorithms, lookup tables, polynomials, low-degree polynomials, Taylor and other shift methods, or combination of them. The question is, can we make it faster? The answer is pretty much the same like for the, as I did for the SQRT. And as you can see, this is the classical Mitchell algorithm, which is pretty fast and very good. And doing some combination of the methods, which is in my case, is the combination of bit manipulation techniques. So knowing a little bit the architecture of the processor, knowing how the fuse, multiply, and add is constructed on the Intel processors, or the graphics subsystem, the IPU, you can get the very nice result comparing to the same function, software-driven, and comparing to the hardware-driven function, which you have from the standard CMAP library. So if you look on this polynomial third degree on the 60 segment with the magic number combination, I am able to get this in the 6th cycle, and the Sun microsystem in the 24. So as you can see, is the 4 times faster, or 2 times faster to the any other algorithms. In terms of the precision, I'm pretty much the same like they are. They 19 bits. This is absolute error, and this is calculated from the absolute error. So we are pretty much the same like they were. So 19 bits precision, and mine is also 19 bits, almost 19 bits. To precision, of course, because it's the piecewise approximation in the different segments. My RMSD is a little bit different than this one, which is obvious here. But if you don't need to have the system with the such precision like 19 bits, let's assume that you have the single the half precision calculation. This algorithm, implemented in software, is the 4 times faster and provides you the precision, which is even doubling the required one. So this is something what I'm working on the daily basis. Hopefully, is the something what might be interesting also for you. Of course, is there many other aspects of the computer arithmetics which we can discuss, like precision, the gap, range, rounding, how we are doing the rounding, what are the formats of the computer arithmetics. So it can be, 16-bit, it can be 32, 64-bit, but what about the B-float or more and more important floating point 8 bits? Is the 8 bits enough for you? How it is, handled in terms of the different format? All this aspect we can discuss in the details, and is a lot of area of the simply computer arithmetics calculation, which may bring a lot of attention benefits, and also good research area, collaboration of the articles, which we may collaborate, especially for the people who are looking for the low precision, small devices without the hardware implementation of the transcendental and the elementary function built in, like microcontrollers, some small devices for the IoT, some FPGA constructs, whatever you are planning to do. And this is something what I was thinking and working during last 2 years at GraphCo. And of course, one of the very interesting aspect I was working on, it was something as the rounding, how we are rounding the numbers from the classical approach, the nearest to zero, nearest, and they were the most popular one. But especially in the machine learning, when the rounding plays a very important role, you need to be sure that is the 0 or 1 or true or false. We're more and more working on the stochastic rounding, and the stochastic rounding gave us better rounding around the very intensive type of the machine learning algorithm scenarios. So we were much more precise to the reality everywhere when the rounding is needed. So this is the end of my hour. And I'm open for questions and answers if I have any.